All right, so we're in the crux of talking about intermolecular forces and learning about why certain compounds dissolve with others, why certain materials are soluble in others, right? And here's a question for us. Which force below is the strongest intermolecular attractive force?
Dipole forces are strong. London dispersion forces are not strong. Hydrogen bonding is stronger than dipole. I don't know about ion dipole. Where does that fit in?
Well, ion dipole is not as strong as hydrogen bonding.
Okay, so hydrogen bonding should be the strongest.
That's right. Hydrogen bonding will be the strongest. Good. So, just a little reminder here. Intermolecular forces. Increasing intermolecular forces increases the melting point, makes it a higher value, right? Because it becomes harder to melt, more energy needs to be going in, higher temperature needs to occur. Increases the boiling point, the density, it becomes more likely to be a solid or a liquid if it has increasing intermolecular forces. It also increases what we call surface tension and viscosity. And vapor pressure, rate of evaporation, these decrease. Okay, so we'll talk about what the term vapor pressure means in the future, but the rate of evaporation, right, how quickly something evaporates, you can imagine a surface of water molecules. Have you ever put a cup of water in the corner of your kitchen, and then gradually over time you see that it slowly seems to disappear?
Yeah.
Do you know the boiling point of water that goes from liquid to gas?
Isn't that 100 degrees Celsius?
That's right. Water boils at 100 degrees Celsius or 212 degrees Fahrenheit. Why does the water slowly disappear? Where is it going?
It's evaporating.
Did the temperature get up above 100 degrees Celsius?
Maybe sometimes.
No, that's 212 degrees Fahrenheit. It would never get up that hot just sitting in your kitchen.
Well, why does it evaporate?
Well, what happens is, if I look in closely at the water molecules along the surface, all right, they're all holding tight to each other, right? But every once in a while, one will find itself in a situation where, with a little bit of help from the nitrogen gas, the air that's around it, right, comes and bumps it off, and it'll fly away. I'm free, I'm free. That's what they say when they get knocked off the surface and fly away, right? And so that's evaporation can occur even though you're not at the boiling point of a liquid. And the rate of that evaporation decreases, however, if you have a very strong intermolecular force. All right? I don't know if you've ever looked in your medicine cabinet to see what other kinds of chemicals you have other than water, but one of the major types of chemicals is an alcohol called rubbing alcohol or isopropyl alcohol. This alcohol, I don't know if I remember one time in my life I took the lid off for something and I left it out on the counter and I came back and it was almost all gone. It had evaporated very quickly, right? Because, well, what does that mean about the intermolecular forces if it evaporated really quickly?
Let's see. If the rate of evaporation was high, that means it didn't have very strong intermolecular forces?
That's right. The molecules could jump off the surface relatively easy. Okay? If you increase the molar mass of a compound, then that will increase the melting point. It'll decrease the rate of evaporation, stronger intermolecular forces, right? The length of the molecule, same thing. Increases the intermolecular forces. All right. Which forces below increase in strength as the molecular weight of the compound increases?
Well, I guess the dispersion forces is the one, right? That has the, yeah, because those are just induced dipole. They're very momentary, very transient, right? Short-lived.
That's right. So dipole forces, if the compound is big, that dipole force doesn't change necessarily. Ion dipole forces, same thing. Hydrogen bonding, same thing. London forces really is the one that depends on the molecular weight. Look at this. This is very interesting. See, neon boils at 27 Kelvin. Fluorine gas boils at 85 Kelvin. Argon, 87 Kelvin. And you can see the difference between neon and argon, right? Now let's bring up the periodic table so we can kind of reflect on this while we're talking about it. Neon and argon, these are noble gases, right? And neon as a gas is just Ne, it's not Ne2, right? But you can see the change in boiling point for our noble gases, neon, argon, krypton, xenon, as we move down, right? And as we discussed before, the change in the boiling point of fluorine, chlorine, bromine, and iodine. You know what room temperature is?
Is it like 25?
Yeah, it's like 22.5 or 20, or in between 20 and 25 usually. And for Kelvin, that's 298 Kelvin. For 25 degrees, 298. So you see here, chlorine evaporates at a temperature lower than room temperature, but bromine is a liquid, as we mentioned. It needs to get up to 332 degrees to boil it. And iodine is a solid, and to melt it, I don't know what the melting point is, but to boil it, you need to get all the way up to 458 Kelvin, which is minus 273, right? A little, almost 200 degrees Celsius. Okay. So, surface tension. Let's talk about surface tension. Okay? Surface tension is something that occurs between molecules, and again, it's related to intermolecular forces, therefore. And the result is molecules will kind of stick to each other. Now, water has a very high surface tension because it has a very strong intermolecular force. But usually we don't see this surface tension very much unless it's on a specific, kind of a surface or in a specific situation because gravity is around. But this surface tension can be really augmented in the presence or up in space where there's no gravity. Okay? So watch this little video.
So here's a common question. Can you cry in space? Do tears work? Well, let's try it out. I can't cry on command, but I'm going to take some water, drinking water, put it in my eye just as if I was crying. Let's see what happens. Get myself nice and stable for you here. Here we go.
So there's no gravity to pull the tears down, right?
So, just as if I started crying, my eye is full of tears. But you can see it just forms a ball on my eye. In fact, I can put more water in.
Why isn't
So
it
if you keep
flowing
crying,
away?
you just end up with a bigger and bigger ball of water in your eye.
The surface
Until
tension is
eventually
stronger than the gravity.
Crosses across your nose and gets into your other eye, or evaporates, or maybe spreads over your cheek, or you grab a towel and dry it up. So yes, I've gotten things in my eye. Your eyes will definitely cry in space, but the big difference is tears don't fall.
Okay, so because there's no gravity, the surface tension then becomes the prominent force, and the water molecules hold together fairly well, right?
That's weird.
Viscosity. Viscosity is a measurement of how quickly something flows. And the larger the molecular force, the intermolecular forces, the higher the viscosity. Something that has a very high viscosity that we deal with in the kitchen is honey, right? Honey is basically sugar molecules, and those sugar molecules stick together very well. They have lots and lots of hydrogen bonding opportunities. And so it results in a very viscous, high viscosity condition, right? Water sticks together pretty well, but it's not as large as honey, and so you don't have as much of those intermolecular forces. So here, intermolecular forces, both hydrogen bonding and dispersion forces, result in a change in viscosity. Wetting is another phenomena. You've seen water placed on top of oil, maybe. It kind of balls up like that. Depending on the type of surface you put it on, though, if you change the surface, you can get the water to spread out or to ball up, depending on how well the intermolecular forces, how similar the intermolecular forces are between the two surfaces, the two substances. Water here, and then we have a hydrophobic surface. Here is water just on glass, which is, again, a relatively hydrophilic. Intermolecular forces that are dipole-dipole. Here, your intermolecular forces, there's a layer, which is just London dispersion forces. Here is our surfactants that we talked about previously. A long chain of carbons. Now, each one of these represents a carbon. The hydrogens aren't shown, but you know that each carbon has to have 4 bonds to it. So if I see a carbon right here that has 2 bonds to it, there must be 2 more hydrogens there. This region of the soap is very hydrophobic. It has only dispersion forces. But what about this region? What does it have?
That can dipole-dipole, right?
That's right. It can dipole-dipole. So we have dispersion forces here and dipole-dipole here. That's a surfactant or a soap. Here's another example. Long chains, which have dispersion forces, and then a dipole, a portion of the molecules that can undergo dipole-dipole interactions. These are pictures of the micelles that we described, with which side is in the inside. Is it the hydrophobic London force dispersion forces portion, or is it the head?
The London forces are in the middle.
That's right. The polar water molecules are all on the outside, and it drives the formation of these micelles with the hydrophobic centers and the hydrophilic heads on the outside. If you dissolve soap in a hydrophobic solvent, something like octane, then these micelles will still form, but they'll change. They'll form the other way. So the positively charged dipole-dipole interacting materials will all be in the middle, and the hydrophobic surfaces will be exposed to the hydrophobic solvent on the outside. Okay, so in terms of solubility, which one would you expect to be soluble in water?
Oh,
sorry, it's not expected to be soluble.
Oh, you're not expected. I was going to say, because HF should be soluble in water. We just said it could hydrogen bond, and CH3OH can also hydrogen bond, right?
That's right. So which one is not?
Oh, the CH4. CH4 can't.
That's right. It's not soluble in water because it can only undergo London forces. Okay, good place to stop. Good work.